Let's start our morning session, and it's a pleasure to introduce John Beck-Song from KIAS, and he'll talk about toric varieties associated with partitioned weight polytopes. Please, John Beck.
Okay, thanks very much for this invitation, and it's my pleasure to be able to speak about my recent joint work with Tachiya Horiguchi and Mikhail Masuda and John Sharesian, which is about toric varieties associated with partitioned weight polytope. So, before I begin, let me first tell you some history about this project. So probably about a year ago, we were trying to understand certain combinatorial coincidence between two different looking objects. One is toric obifold, and the other one is Hessenberg, certain Hessenberg varieties. So, and eventually, we could find a nice family of polytopes, which explains the situation. But somehow we could not find any literature which explains, which studies this family of polytopes. So, so from the purely combinatorial point of view, we would like to understand more about this polytope. So it would be very nice if we can discuss this polytope in a framework which is well studied or well known. So before I begin my talk, I will show you some three-dimensional examples of these polytopes, and then please let me know later if you have ever seen this polytope in your research, or if you know any other categories of this polytope. Okay, so yeah, so this is the polytope, three-dimensional. So one F vector is 12, 18, and 8. So this. Okay, this is vertices and edges and faces. So it consists of 4 squares and 4 pentagons. And another polytope is this three-dimensional and 11 facets and 4 squares, 4 pentagons, and 3 hexagons. So another class of polytopes is given by like this. Looks a little complicated, but it is 5 squares, and facets are given by 5 squares and 2 pentagons and 4 hexagons, and it has 18 facets. Looks a little complicated, but anyway, something like this. Okay, so let me explain how this polytope arises in our project. So okay, let me begin with the basic definition of convex polytope, so which is the convex hull of the vector point in a vector space. And if you think of the lattice structure in your vector space, then if you take your point as a rational point, then we say that this polytope is a lattice polytope. Okay. So my example is Permetohedron. So you take a point in a vector space by the Weyl group, a symmetric group orbit of this point, 1, 2, okay, 1, 2, n. So totally you have n factorial many points in a vector space, and to take a convex hull, this is the Permetohedron. So when n is equal to 2, you only have 2 points. 1, 2, and 2, 1, which gives you the line segment. And when n is equal to 3, then you begin with 1, 2, 3, and you have 6 vertices, which gives you regular hexagon in some affine hyperplane in R3. Okay, so this is just a well-known definition. And so this is the reason why I consider this lattice polytope. So I'm looking at some projective toric variety from this lattice polytope. So what is the toric variety now? So toric variety is an algebraic variety of a complex containing an algebraic torus theta n as a dense open subset. And there is a natural action on this. There's a natural action of this algebraic torus on the theta n dense open subset, and this action has to be extended to an action of this variety. So that is the condition for this toric variety. So even if it looks a little complicated, but the situation can be summarized by this diagram. Okay, so first you have this multiplication on this algebraic torus, and then this multiplication has to be extended to an action of this variety. Okay, so the easiest example is going to be when n is equal to 1, you have, you can think of the C star, and then by adding the origin at this C star, you can, your toric variety can be C star itself, or by adding the origin, you have this complex plane, or if you add one more point, infinity point, then you have this projective space. So this projective toric variety CP1 corresponds to this line segment, a one-dimensional polytope. And when n is equal to 2, you have CP2 or CP1 times CP1 and or CP2 with connected sum of CP2. So each of these corresponds to triangle. Because n is equal to, I have to have two-dimensional polytope. So in this case, triangle or square of some in general n-gon. Okay. So today I want to focus on the cohomology of this toric variety. This is the general description of a toric variety, cohomology of the toric variety under this condition when the toric variety is coming from the simple polytope. This restriction gives you the restriction on the toric variety, which has to be a smooth toric variety, or so at worst orbifold singularity. But in this case, toric, the cohomology can be expressed by the truncated polynomial ring, and each of these facets contribute degree 2 generator. Okay, and then you have two types of ideas. One is this contains the information of the geometry of this polytope. So what is the geometry? This is nothing but the some normal vector of the defining equation of this facet. Okay, and J is the Stanley-Rigen ideal, which contains the combinatorics of this face structure. So if you have a bunch of facets and this J determined by the what kind of facet they do not intersect. Okay? So I will come to this formula again later. All right, this is just a general background about my talk. And okay, so let me introduce one of our main objects, which is the weight polytope. So just remember the definition of Permetohedron, which I showed you several slides before. So what was that? There was the you take a point n 1, 2, da da da, and an n, and then you take a symmetric group action on it, and then take a convex hull. So if we look at this symmetric group as a Weyl group corresponding to the root system of type A n-1, then you can naturally think of the other Lie type Permetohedron. Okay, so if you have the root system of rank R, okay, and then you have to you may think of the rate lattice and its root space, and then Weyl group, and then if you take a point in this vector space E, and then take a convex hull of this Weyl group orbit, then this is called weight polytope. Okay. So for example, if your point is 1, 2, da 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 n, and then if you take a Weyl group of type A n-1, then that is going to be the definition of this Permetohedron. Okay. So, all right. So in order to understand this weight polytope, we have to study a little bit about the root system. So let me just review a little bit about this the classification of root system. I'm just looking at the classical Lie types. So root system is defined by classified by the Dynkin diagram. So I just draw here, okay, and I take a in order to define a root system, I have to have some vector space here. So in type A, I take some n-dimensional vector space in subspace in Rn plus 1 given by this equation. And in type Bn and Cn and Dn, I take a n-dimensional subspace in R2n given by these equations. Okay. About the Phi group, for type A and this is the symmetric group, and the symmetric group is generated by simple transpositions. Then we are looking at this simple transposition by the reflection on this vector space. The way how we understand this is just permuting ith coordinate and I plus first coordinate in the vector space. Okay. In type Bn, this is a subgroup in a symmetric group on this kind of set. This n bar means the set of 1 bar, 2 bar, n bar. And this Phi group is sometimes called signed permutation. So each of this transposition is given by something like this, and Sn is slightly different from the others. And type Dn Phi group is sometimes called evenly signed permutation group, but but each of this generator is same as type B, but Sn is slightly different. Okay, but whatever the type is, eventually it is generated by simple transpositions, S1 and Sn. So, but S1 and each of Si is different from the types. But the parabolic subgroup is just you take some subset of this generator. So this is parameterized by the subset in N. So whenever you take a subset in N, you can think of the parabolic subgroup generated by this SK. Okay. All right. So, all right. This is the example of type A Permetohedron. Okay. So we already have this P to the A2. So A2 root system and Permetohedron. This is nothing but hexagon, and A3 Permetohedron is something like this. This is Permetohedron again, and in type B case, you first begin with this 1, 2, 3, 4 in R4 space, okay? And then think of the Phi group action on it. So signed permutation group. So 1, 2, 3, 4, and then if you have S1 action, this point goes to this one, 2, 1, 4, 3, and maybe S2 gives you this point. So swapping these two, okay? So eventually, taking all the orbit of this 1, 2, 3, 4, you have this octagon, okay? And then this is the three-dimensional example. Here is the type D case. So in this case, in 2 dimension, you have the square, and 3-dimensional case, you have this one, okay? One observation is, right, so let's go back to, okay, before that, even if it looks the most basic example, but there is one more easier example than this. What is that? There is the P to the A1, right? So there was the line segment, okay? But the reason why I showed you, why I'm telling you this type A1, because if you look at this D2 type, then let's go back to this Dinkin diagram again. Then what is D2 now? So D2 is just a 2 point, right? So this 2 point gives you, this 2 point is exactly A1 times A1. So maybe this is exactly the product of these two line segments. So the reason why we have this Permetohedron as a square, the I2, the product of line segment, because there is the D2 root system is isomorphic to A1 times A1. So similarly, we have D3. What is the D3? We have this root system. This is isomorphic to A3. So even if these two are slightly different, but combinatorially they are same. You have this hexagon here, and this hexagon is connected by 3 square faces, something like this. And we have another hexagon here, something like this. So yeah, they are same. So the type D case, it makes sense after D4 maybe. So we can study this one by the type A case. So okay, so as I told you before, by looking at this polytope, I'm looking at this toric variety, and in order to, and among the toric variety, I'm going to look at the cohomology. And in order to see the cohomology, I have to understand the combinatorics and geometry of this polytope. So because of the time limited, let me just focus on type A case today. So this is the definition of this Permetohedron of type A, and this is the sitting n-dimensional polytope sitting inside this hyperplane in Rn+1, a fine subspace in Rn+1, and there's one-to-one correspondence between the zero facet with the non-empty proper subset in n+1 set. Okay, and the facets are given by some convex hull of some point, or you can describe this facet as some defining equation. The reason why I showed you this is I need this normal vector to define the cohomology, to present the cohomology. Okay, and two facets they intersect whenever two indices are one is the subset of the other. Okay, so this we can understand. We can fully understand the combinatorics of the facet structure, and this Permetohedron is a flag polytope. So let us look at the toric variety corresponding to this Permetohedron, which is called Permetohedral Variety. So this is smooth toric variety, and its cohomology is given by, like I said before, the cohomology generators are parameterized by the facet, and facet is corresponding to non-empty proper subsets in n+1 set. So I have the degree 2 generator for each subset here, and I have I and j ideas. Okay, and these are I has something to do with normal vector, and then j has something to do with phase structure. Okay, and yeah, so this is just a formula itself. You don't need to pay attention to all these details because I'm not going to get into the details of this computation, but somehow I want you to focus on this observation. Okay, so there's a nice symmetric group action on this cohomology by each of this generator. And so if you take an element in this symmetric group, it acts on this generator by acting on this index. Okay, so yeah, so to tell the truth, this action induced from the action on this variety itself, but today let's focus on the cohomology, the action on this cohomology. So since we have this symmetric group action on this cohomology, we can define a parabolic subgroup action on this cohomology from this section. Okay, so today I want to look at this ring of invariant. So one important proposition is this ring of invariant is generated by this one. Okay, just this is nothing but the orbit summation of this orbit element. Okay, all right. So by the way, this action, you can think of this action in this from the geometry, like action on this variety, but somehow if you just look at this algebra level, it's not that obvious because I am defining this equation only on this generators of this polynomial ring, but somehow we have to see that whether these two ideas are invariant under this action, but that's something we can do by hand. Okay. All right. So any questions so far? Okay. So, okay, let's go to some other definition. So this is the Y group as before, and this is parabolic subgroup as before. And in order to define this weight polytope, partitioned weight polytope, I have to take one more, some other definition, which is I denoted by this HK given by. So again, I'm going to look at this type A case. So we have a vector space element, and then I'm just looking at the hyperplane given by this equation. Okay. So what is this equation? Remember that this Y group acts on this Rn plus 1 by permuting its coordinate. Okay. So this HK is nothing but the invariant subspace with respect to the SK action. Okay. So here I have SK action. This permute kth coordinate and k plus first coordinate. So if this equation, the hyperplane given by this equation stays same under this SK action, and because this hyperplane divide the Euclidean space into two parts, and I'm going to take one half of this, one of these two parts. So HK plus is the closed half space given by this hyperplane, right? So so my partition weight polytope associated to this subset, if first you prepare this weight polytope and then you take an intersection corresponding to this intersection of these half spaces corresponding to this K, capital K, which you take for this parabolic subgroup. Okay. So in type A example, the easiest example is probably this one. You begin with hexagon, which is type A Permetohedron, A2 Permetohedron, and then let's write something. So this line is your H1. Okay, so you swap first coordinate and second coordinate. So this hyperplane is invariant under this section, and then you take a Permetohedron and then intersection with half of this, right? And then A2. So if you take your capital K by 2, then this is the half space, and then this hyperplane is the invariant part of the action given by the permuting second and third coordinate. And then eventually you have, if you take 1, 2 as a, if you take the K as an entire set, 1, 2 in this case, because I'm looking at A2 type. So in this case, you have this square face, square part. So so A3 case, I have the 3. So I'm going to show you the 3 examples, and these 2 are examples which I showed you in the first page of my slide, right? And then this is some other. So this is, look at this. In A3, by taking 1, 2, 3, what does this mean? This means I take capital K as an entire set, 1, 2, 3, right? So in this case, I don't know whether you can see this or not, but it is 3-dimensional cube, right? So whenever you take an entire set, your capital K is an entire set, then you will have the identity component in the cubical decomposition of this Permetohedron. So what do you mean by identity components. I first begin with 1, 2, 3, and 4, right? And then take a while group action on it. So I have a bunch of vertices, but this is the 1, 2, 3 for the identity element. And then this cube is the component corresponding to this identity element. So this is again a cube, two-dimensional cube. So 1, 2, 3, right? So this is the type B example. And these two are examples which I showed you in my second page of this slide. And this is the, looks a little complicated, but this is again a three-dimensional cube. And this point is the identity element, 1, 2, 3, 4, 5, 6, 7, 8 in this case. 1, 2, 3, 4, 5, 6, right? So because I'm looking at B3, this is the R6. At this point is 1, 2, 3, 4, 5, 6, the identity element. Okay, so so by this polytopes, I'm looking at the toric variety corresponding to this polytope. So and also I'm going to look at the cohomology of these toric varieties. So in order to see this, I have to understand the phase structure of this. But yeah, so there are two types of facet. So one is the facet coming from the original facet of the weight polytope, and the other one is the facet coming from the hyperplane, which I cut. Okay, so for example, yeah, so in type A case, for example, okay, so for example, this face, this facet is the facet coming from the this invariant subspace, right? Or this facet is a part of the original facet of this Permetohedron, right? So there are two types of facet here. So one is the facet coming from the original facet of the Permetohedron, and the other is the facet coming from the hyperplane, which I cut. And intersection relation is, so we can understand this one. So yeah, just relax and then take a look at it. It looks complicated, but this is nothing. And this is flag polytope. So all this understanding gives me the cohomology of this toric variety corresponding to this weight, partition weight polytope. Okay, so again, I'm not going to take you all these details about this. Yeah, just okay, just think that okay, this guy's worked very hard on computing all this cohomology. Okay, so here is our main theorem. So first we considered the cohomology of the, okay, so notation is, we begin with the root system, okay, in any classical Lie type. And we have some parabolic subgroup, and then we have xk and x and xk, which are toric varieties associated with original weight polytope or partition weight polytope. And then remember that we studied the cohomology of this toric variety coming from the associated weight polytope and its ring of invariant. On the other hand, we considered the cohomology of the toric variety corresponding to partition weight polytope, and then eventually there is a ring isomorphism between these two. Okay, so here's the brief sketch of the proof. Just first, we remember that this ring of invariant is generated by this parabolic subgroup orbit of each degree 2 element. So this is generator of this ring of invariant. And then we could construct a very explicit homomorphism from this one to this one, and then we showed just a subjectivity and injectivity. So the proof is rather straightforward. Okay, so this is our main, one of the main results. And yeah, there are a bunch of interesting viewpoints of this isomorphism, but today I'm going to introduce you some application to Hessenberg varieties. So yesterday in the morning session, Tachiya Horiguchi gave a nice presentation about this Hessenberg variety, and then he, at the end of his talk, he gave some notice about my talk today. But now this is time to introduce our application to Hessenberg varieties. Okay. So in order to I'm going to define Hessenberg variety in some general context. So let me just begin with a connected semi-simple algebraic group over C, and then this is a Lie algebra.
Excuse me, John Beck, back to
Yes.
your previous theorem. That's about rational coefficients with rational.
Yes, yes. Yeah, that is for the rational coefficient. Yes. So okay. I probably forget to mention this, but this xk is in general orbifold. So x is smooth, but this xk is orbifold. So it was a little hard to discuss the integral cohomology of this toric orbifold. Okay. So I believe there is no torsion, but I couldn't prove that. Anyway, so everything is just rational coefficient. Thanks for pointing out this. Okay, so okay, let's go back to this Hessenberg variety. So in order to define a Hessenberg variety in a little general context, we have to begin with a connected semi-simple algebraic group, and G is its Lie algebra, and take a Bourré subgroup of this G, and Bourré subalgebra. Okay, and then in order to define Hessenberg variety, we have to choose certain subspace in this Lie algebra, which is called Hessenberg space. Okay. So this is nothing but the B submodule containing this Bourré subalgebra, and then you can define certain map depending on this choice of Hessenberg space. Okay, depending on the choice of this Hessenberg space, you can define a map from this twisted product to this Lie algebra given by if you have this point in this domain, and then it maps to the adjoint action. Okay, right. So so the Hessenberg variety is nothing but so in order to define Hessenberg variety, you have to pick up the Hessenberg space, right? Oh, there's some, okay, this should be this one, I'm sorry. So it has to contain the Bourré subgroup, and then this is the subspace in Lie algebra. Okay. So you have to pick up a Hessenberg space together with some element in this Lie algebra. This is the element in this target space. And the Hessenberg variety is the pre-image of this map. Okay. So if you interpret this one in terms of type A setting, then this definition coincides with the definition which Tachiya introduced yesterday in the morning session, like Hessenberg function and the linear operator things. Okay. So remember that in order to define Hessenberg variety, there are two ingredients. So X in an element in this Lie algebra, and the takeout and the Hessenberg space H. So depending on the choice of these two ingredients, there are a bunch of names. Okay. So if you take out Hessenberg space by the entire Lie algebra, then this is going to be flag variety. And if you take the Bourré subgroup, Bourré subalgebra, this is called Grothendieck Springer fiber. And you can take an element in this Lie algebra by regular element, semi-simple element, and nilpotent element. Each of these is called regular Hessenberg, semi-simple Hessenberg, nilpotent Hessenberg. So in particular, if you take an element, regular nilpotent element, and then if you take a Hessenberg space by the Bourré subalgebra, together with all the by containing all the negative simple roots, then this is called Peterson variety. And then if you take a regular semi-simple element and then take a Hessenberg space like this, the same Hessenberg space H1, and then this is exactly the toric variety corresponding to this weight polytope. Okay. All right. So let me briefly review some cohomological study of this Hessenberg variety. So during next many years, so there are a bunch of study groups on this, which studies this cohomology of this regular semi-simple Hessenberg variety or regular nilpotent Hessenberg variety. So probably from the symmetric group, bi-group action, bi-group representation point of view, probably this Timochiko's work is the beginning point. So she considered regular semi-simple Hessenberg variety, and then she defined certain bi-group action on the cohomology. And later, Fukawa, Harada, Masuda, and Horiguchi, Harada, Masuda, they showed some nice interpretation of this regular nilpotent case, right? So, so after, I mean, their cohomology computation shows us that this is somehow, this is isomorphic to the toric variety corresponding to this partitioned weight polytope, right? So remember that if you take, this is our capital K. So if you take a capital K as an entire set, then what is the partitioned weight polytope? This is the identity component of the cubical decomposition of this weight polytope. So this is the toric variety associated with some cube with some characteristic normal vector data on it. Okay, so this normal vector depends on the Lie type corresponding to, eventually this corresponds to the Cartan matrix. Okay, but anyway, they showed this isomorphism, even if they didn't mention the partition weight polytope things, but eventually they are isomorphic. Okay, and later, Hirako Abe, Harada, Horiguchi, Masuda, Takuro Abe, Horiguchi, Masuda, Murai, Sato, and they showed regular nilpotent Hessenberg variety. Okay, so here is the H1 Hessenberg space case. But anyway, they showed this regular nilpotent Hessenberg variety is isomorphic to the ring of invariant, okay, with respect to this bi-group action, right? So, so if we combine these two isomorphisms, what we have is what? So regular nilpotent Hessenberg variety corresponding to this H1, and the ring of invariant of this bi-group action on this cohomology of the regular semi-simple Hessenberg variety. And then this is isomorphic to the certain toric variety, partitioned weight, the very particular case of partitioned weight polytope. Okay, so this is all about rather two extreme cases. Remember that if you have a regular element in Lie algebra, then this can be represented by semi-simple part and then nilpotent part. So somehow semi-simple and nilpotent, they are, this is two extreme cases. So what happens if we take just general regular element in the Lie algebra? So recently, Brosnan and Chow and independently by Libano and Crookes, they showed if you take a regular element in the same Hessenberg space, and this cohomology is isomorphic to the ring of invariant with respect to this parabolic subgroup. Okay, and remember that our main result is the ring of invariant with respect to this parabolic subgroup on this cohomology of the semi-simple Hessenberg variety. Remember that this is Hessenberg variety, but if you take a regular semi-simple element and the particular Hessenberg function, this is going to be the Permetohedral variety or toric variety corresponding to weight polytope. So, our main result is exactly this one. So weight polytope, toric variety corresponding to this partitioned weight polytope is isomorphic to this parabolic subgroup ring of invariant on this cohomology. So if we combine these two, this isomorphism and this isomorphism, we finally have the cohomology of the regular Hessenberg variety is isomorphic to the ring of invariant. And then this has a presentation in terms of the toric obifold. Okay. So this the series of isomorphisms extends the previous result, which is about two extreme cases, and then now we have these two extreme cases. It is rather parameterized by the subset in bracket n or in terms of the parabolic subgroups. It can be trivial group or Weyl group itself, or it can be a general parabolic subgroup. So this is the one of the application of our main result one. Okay. All right. So, okay. Thank you for your attention.
Okay. Thank you, John Beck. Let's all thank our speaker. Okay. So, are there any questions or comments? John Beck, have you tried to look at case theory, like invariant case theory, invariant subring for the same polytopes? Are there parallel results for the case theory rings?
We haven't tried that, but yeah, that's a good question. We haven't tried the case theory part, but yeah, that's probably good question to explore.
Because it's like, yeah, that's, you know, well, it's not, of course, yeah, it's not, you have this, I think that the equivalent case theory is naturally somehow, should somehow naturally reflect the representation theoretical part of this story. That there might be some other interesting manifestation of this representation theory if you look at the equivalent case theory rings, or just ordering case theory rings. They both are related in the same way as for the ordering cohomology. And I think Megumi with co-authors, yeah, they've done quite a lot for this case theoretical calculations with toric varieties. So.
Yeah. Right. Yeah. Okay. Yeah.
Well. Right.
Okay. Thank you for the comment. So do you think this we can think of the MU also?
Well, yeah, I think yeah. Once you understand case theory, there should be a similar pattern for arbitrary complex-oriented cohomology theory. Yeah, at least with a cohomology ring of the toric manifolds, it has the same structure of an arbitrary complex-oriented theory, including MU, of course, it's universal. So you just have to replace them. The Stanley-Reisner relations are the same in all theories, and these linear relations, they have to be calculated in the appropriate formal group law. So in cohomology, they're just linear forms. In case theory, you just have to write down that the corresponding vector line bundles are trivial, right? So that's like multiplicative formal group law. And in cobordism, these relations are written in the formal group law of geometric cobordism, the universal formal group law. But the structure is the same. But I don't know about invariant rings. The rings of invariance is something maybe more subtle, even in the case theory. How to write down the analog of this invariant ring?
Right.
That I haven't thought about. Yeah. But in case theory, that should be somehow, I think, because case theory is so much related to this representation ring. So I think there should be some kind of nice way to write down. Okay.
Okay, thank you for comment.
Right. If there are no more questions, then let's thank John Beck again. And yeah, I think we resume in 5 minutes. Yeah, 10:50 Moscow time. Yeah, can you try sharing your slides?
Yes.
Yeah, we can see it.
See? Oh,
yeah,
okay.
maybe can you make it full screen?
Okay.
Well, yeah, if it's okay for you.
Is it okay?
Yeah, I think this way better. Yeah.
Okay, can I start? Or
yeah, that looks good. Yeah, just 1 more minute we wait and then we start.
okay.
All right, I think we can continue our morning session, and it's a pleasure to introduce Jingfang Liang from Fudan University and National University. From Fudan University, just I see.
Yeah.
That's your classes. Yeah, and she'll talk about twisted Milnor hypersurfaces and alpha invariant. Please.
Good morning, everyone. My name is Jingfang Lian, and firstly, let me thank for the organizer give me this chance to give this talk here. And my talk will be about the alpha invariant of the twisted Milnor hypersurface. And in fact, we are still working on more problems on the twisted Milnor hypersurface, and the alpha invariant is just the first one. And let's look at the outline of this talk. In the first part, I would just give a very brief introduction of the background of the alpha invariant, and then I will give the basic definitions and properties of the twisted Milnor hypersurface, and then I will give a brief introduction of the current situation of alpha invariant. And the following 4 parts are some of our works about alpha invariant. And if a manifold which is simply connected, closed, and dimension less than 5, in 1980s, Gromov-Lawson gave a result that if M not spin, then this manifold carries a positive scalar curvature, which we here just denote PSD. And in 1992, Stolz gave that if M is spin, then the manifold carries positive scalar curvature if and only if the alpha invariant vanishes. Combined with these 2 results, we can get that if the manifold is simply connected, closed, and dimension less than 5, if it is of positive scalar curvature, then this manifold either not spin or spin, and its alpha invariant vanishes. Thus, we mainly consider spin manifold. And in fact, in the later part, I will talk about the definition of alpha invariant. The alpha invariant is defined on the spin manifolds. And in 2009, Fang and Shao calculated the alpha invariant of complete intersections of projective space, where they mainly using John's formula in the most difficult case. Here we also use John's formula. I would introduce in more detail in the later part. Before discussing more about the alpha invariant, let's look at the twisted Milnor hypersurface. Before that, let's recall the Milnor hypersurface. Milnor hypersurface is a submanifold of CPN1 times CPN2, which is a trivial projective bundle. And more exactly, it is defined by an equation where the xk and yk are all the homogeneous coordinates, And if we that U and V are two generators, then the MIAN hypersurface is just the Poincare del to U plus V. And accordingly, we can define we here defined the twisted projective bundle V as the projectivization of N2 plus 1 plane bundle, and where the eta is the tautological line bundle, and the C with underlined is the trivial bundle over CPN1. And here the eta tensor I means I's tensor of bar of eta if I is positive, and if I is negative, it is mean the tensor power of eta bar, where the eta bar is the conjugation of eta. And therefore, we can also define the twisted MIAN hypersurface as the Poincare del to d1u plus d2v. And to better know about the twisted MIAN hypersurface, let's see a case. For I is O0, where the black I is a sequence of integers. If it's O0, then the twisted MIAN hypersurface is a hypersurface of V, where V is the trivial projective bundle. And furthermore, if we that D1 and D2 are O1, then the twisted MIAN hypersurface is just a MIAN hypersurface. And in fact, projective bundle can be viewed as a toric variety or quasi-toric manifold. And for the trivial one, the U and V, as we all know, just the first chain class of a complex line bundle, where the eta 1 and eta 2 just the tautological line bundle over its corresponding projective space. And CPN1 times CPN2 can be viewed as a quasi-toric manifold with the following characteristic matrix, which is a block diagonal matrix. Each block is a characteristic matrix of a projective space. And for V, the two generators are almost the same. The difference is gamma here. The gamma is the tautological line bundle over V, which V is the total space of this projective bundle. And V can be viewed as a quasi-toric manifold with the following characteristic matrix, which is not a block diagonal matrix. The difference is the red numbers that are not always 0, and this red number just the sequence of integers. And in fact, the twisted MIAN hypersurface is simply connected if we assume it is with dimension of less than 5, since by 1972, Kato Matsumoto gave a result told us that there exists a submanifold which is just the twisted MIAN hypersurface, and its corresponding homology class del to d1u plus d2v. And the twisted MIAN hypersurfaces can be simply connected. And till now we discussed the basic definition and properties of twisted MIAN hypersurface. If we assume the dimension is not less than 5, then it's naturally simply connected. And since we want to study the alpha invariant of it, we need to know what's the sufficient and necessary condition for the twisted MIAN hypersurface spin. And spin, by definition, is the first Chern class is 0 by module 2. And by definition, the twist-muon half surface is Poincare del2 d1u plus d2v, which means there exists a complex line bundle over V, such that the first Chern class of this complex line bundle is just the d1u plus d2v, and the normal bundle of this twisted muon half surface in V just the pullback of this complex line bundle. With the normal bundle clear and the twist muon half surface is the submanifold of V, we can know that the tangent bundle of V restricted on the twisted muon half surface is isomorphic with the tangent bundle of twisted muon half surface, or plus with its normal bundle. Therefore, we can get the Chern class of the twisted muon half surface, which is expressed by the Chern class of V and the Chern class of L. L is can be expressed its normal bundle, and therefore we can get its first Chern class, which is just the first Chern class of V minus d1u minus d2v. And in next page, I will explain in detail why the first Chern class of V is in this style. And therefore, we can get the first Chern class of the twist muon half surface, which is just n1 plus 1 minus sigma 1 minus d1u plus n1 plus 1 minus d2v. And by definition, if we want to know what's the sufficient and necessary condition for the manifold spin, which means the coefficient of u and v in the first Chern class all need to be even. It means there exists K1 and K2. I here denote K1 and K2 as the even number. Therefore, D1 and D2 can be expressed by these two even number. And let's look at the Chern class of V. In 1958, Blair and his group give a result. Give a clear description for the projective bundle. It gives the tangent bundle, and it's a homology structure, and applied to V is just like this. Here I will not say more about its cohomology structure, even though it is important in our calculation. Since the time is limited, I will just explain the first Chern class of V in detail. So from this result, we can get its tangent bundle can be expressed by its base space and its fiber. And since the gamma pi is the complex conjugation of a topological line bundle, it's a line bundle tensor. The sum of some line bundles can be split up as the sum of some tensor bundle of two line bundles, which is clear for us. Therefore, we can get the Chern class of V is the Chern class of projective space and the tensor bundle of these line bundles. Therefore, we can get the first Chern class of V. And after talking about the basic properties and definition of twist muon half surface, let's look at the alpha invariant. Alpha invariant, just as I mentioned it in the beginning, is defined on the spin manifold, which is defined as a Thiel-Singer invariant, which is a homomorphism from the spin cobordism ring to K theory. And where K theory is, as we all know, is 8 periodic, and K theory is 0 for n is 3, 5, 6, 7 by module A. And in fact, alpha invariant is closely linked with A hat genus. Since in the most cases, in the first 3 cases, the alpha invariant is clear, either 0 or expressed by a hat genus of itself. And why is the calculation of alpha invariant is difficult? Is because the fourth case for dimension 2 module A, there's not an explicit formula here. But in 1993, there's a formula of John give for the manifolds whose dimension is just 2 module A. The manifold here say H need to be a submanifold of V, and it is point care del to a degree 2 homology class of V. Then the alpha invariant of H can be expressed by the hat genus of V and the cohomology class. And in 2009, just as I mentioned in the beginning, Fang and Shao give the result of complete intersection of projective space. And in particular, when the dimension is 2 module A, they used John's formula and give an explicit formula for the complete intersection. And for our study objects, the twist-muon half surface, it is always with dimension even. And so we can conclude that the alpha invariant of the twist-muon half surface is either 0 or expressed by a hat genus of itself, or we can use John's formula to calculate it. So throughout our calculation, we first calculate a hat genus of the twist-muon half surface, and then in the spatial dimension, we give the alpha invariant. And here is our result. First, we define a formula F with some index D1 and D2 is expressed its point care del to the cohomology class, and the formula is expressed as the sum of the multis of some binomial coefficients, and where the M is the sum of Mj and L is the sum of Lj, and the binomial coefficient of vector L and vector M is the multis of some binomial coefficients, and the multi of vector M and vector L is similar. And what I still want to say again is in page 8, in fact, we give the sufficient and necessary condition for the twist-muon half surface spin. The D1 and D2 can be expressed by K1 and K2. So the result here can, this formula we define here can be expressed by K1 and K2. But what is needed to pay attention is only when the twist-muon half-surface is spin, can the Ki can be integers. The first result is for its A genus. What's interesting is that the A genus of this muon half surface can be expressed by f d1 d2 minus f minus d1 minus d2. And for the spin twisted muon half surface with dimension not less than 5, in the special dimension, we also give its formula. It's just the formula we define here, f by module 2. To know better of our result, let's look some simple examples. For the sequence of integers are all 0, then the twist muon half surface is just the half surface of CPN1 times CPN2. And Ki and Di can be expressed by each other. And in this case, the formula f can be very easy. It is just a multi of 2 binomial coefficients. And we can also give the A genus of it. It is also simple, and if we assume the twist muon half surface spin, then we can give the sufficient and necessary conditions for the A genus vanished. What here I need to emphasize is that we need to assume it's spin, since only when it is spin, K1 and K2 can be integers. If it's not spin, the result expressed by D1 and D2 can be all integers, but the result is not always an integer. And for the twist muon half surface spin, and in the special dimension, we can also give the alpha invariant, which is just also easy, and the result or the expression is similar or is the same with the result of Wei Pinzhang in 1996. Where he give the alpha invariant of the spin hypersurface of projective space, and its result is the same with us. And as for examples for the muon half surface, we can easily get the sequence of integers are all 0, and D1 and D2 are all 1. Then use our formula, we can give the A genus of it always vanishes, which matches with the result of his proof in 1994. And if we assume it's spin, we can also discuss its alpha invariant. And what need to pay attention is D1 and D2 are 1, which means K1 and K2 can be minus half of N1 and minus half of N2, which need to be integers, which means N1 and N2 are both even. Therefore, the alpha invariant can be just the multi of 2 binomial coefficient and all 0, since binomial coefficient the upper number if it's integer, and less than the lower number, then it's 0. And combined with alpha invariant vanished, the spin muon half surface always vanish, always emits positive scalar curvature. And it is interesting is that if the sequence of integers not always 0, but we still assume D1 and D2 is 1, and the twist muon half surface spin, we can get its A genus and alpha invariant still vanishes. And in this part, I would say something about the application of a heterogeneous and alpha invariant. First is the circle action. In 1970s, Attila Hissbruch gave a result that if circle acts non-trivially on a connected spin manifold, then the heterogeneous vanishes. Here we give some examples for the heterogeneous not vanished, and it is also spin. For the sequence of integers are all zero, we just discussed in the examples. We can also give its sufficient and necessary conditions non-vanished for the heterogeneous non-vanished. And for the sequence of integers not always zero, say just one number is not zero. We can also give a lot of examples not vanished. Combined with a result of Attila Hissbruch, we can get that there does not exist non-trivial circle action on these examples above. And another application of a heterogeneous I want to say is from Hissbruch, Berger, and John in 1994. This theorem described a fiber bundle for the fiber is compact oriented spin, and the structure group is compact connected Lie group. Then every elliptic genus can be expressed by the ellipgenus of its base space and fiber space. So since a heterogeneous is also ellipgenus, so the heterogeneous of any odd dimension projective space fiber bundle over projective space always vanishes, where the odd dimension projective space, since a heterogeneous of projective space is zero if and only if n is odd. And by the way, even if the dimension is even, it is not a spin manifold. So combined with the result of Hissbruch, Berger, and John, we can get in general the trinomial half surface is not equivalently cobordient to odd dimension projective space fiber bundle over projective space. And here is the application to positive scalar curvature of alpha invariant. Since we give the formula of alpha invariant, we here give for n1 and n1 and n2, but n1 is 1 or n1 is 2. Give its characterization of the positive scalar curvature. And from this result, we can get as much as examples for the trinomial half surface without positive scalar curvature. Let's compare the muonal half surface and the trinomial half surface. If the muonal half surface is spin and dimension less than 5, its alpha invariant always vanishes, and which means it always emits positive scalar curvature. And for the twisted one, it is not always zero, and which means it is not always emits positive scalar curvature. And for a heterogeneous, the muonal half surface always vanishes. And there's a property of muonal half surface. There always exists non-trivial circle action on muonal half surface. But for the twisted one, it is not always zero, since we give a lot of examples. And therefore, there does not exist non-trivial circle action on these examples. And And in this part, I will say something more. May not concerned with twisted Miller hypersurface. During the calculation, we found a very interesting binomial numbers, which we defined A and M. We study its recurrence, explicit formula, and a generating function. It may be of potential meaning, and it may be of interesting in the number theory. And with further investigating, we also found there are some closely links with some important binomial numbers in number theories, such as the Stirling number of the second kind, the Bell number, and the Bernoulli number, and it can also be expressed by the difference. And in fact, using our method to calculate alpha invariant, we can also give the alpha invariant of hypersurface of generalized Bott manifold. Since the time limit, I will not say much for the generalized Bott manifold. I just say it with the following characteristic matrix. It is also not a block diagonal matrix, and under all this -1, all the numbers under them are integers which are not always 0. And we can also define a spin submanifold of M, and we define it as H. It is Poincare del to D1U plus D2V. And other notation are similar. Then we can also give the alpha invariant and a head genus of this submanifold. And in fact, in the beginning, I mentioned that we are still working on some other problems like ellipse genus for real and complex cases, and Witten genus, and so on. That's all my talk today. Thank you for your listening.
Thank you very much, Jingfang. Let's thank the speaker. Are there any questions? So you mentioned that you first want to know whether this twisted generalized Milnor hypersurface is spin. And I'm wondering, can it ever be SU? So can actually S1 vanish, not just modulo 2, but can it just vanish as an integer characteristic class?
It's a good question, and in fact we are considering, we are still want to consider more problems and cases, but till now I don't consider about the integers, just module 2.
Yeah, I think because that's precisely what we were doing with Professor Lu, Ji Lu, that we were interested in finding some kind of special unitary to SU quasi-toric manifolds, and also those generalized Bott manifolds are somehow the place where you can find them. So, but then you are looking at this hypersurface dual to some Poincare class, like Poincare dual to some simple cohomology class, like the linear combination of the standard generators, and actually you may be able to find more SU manifold there, which not just spin. Yeah, I understand that your motivation was originally some kind of differential geometrical results about the positive scalar curvature, and it's related to the spin structure. But SU structure, I think, is equally interesting. I think you might be able to find SU manifolds among them, not just spin. SU means just C1 vanishes identically, not modulo 2, but identically. C1 is 0. First Chern class is 0, yeah.
Oh, thank you.
Okay, well, I think, yeah, Professor Lu knows a lot about this. It may be another thing to look at. Anyway, thank you. Yeah, are there more questions? If not, let's thank Jingfang again. And yeah, the next talk will be 11:50 Moscow time, so we have 25 minutes for coffee or please, Lisu.
Thank you. Thank organizers for the invitation. In this talk, I will introduce an integral orbifold cellular homology of a Coast orbifold. And this talk is based on a joint work with Professor Zilü and Li Yu. This talk is divided into 3 parts. First, record some basic definitions of orbifold and Coase group and Coase orbifold. Next, I will review some Coase homology series of orbifolds and introduce our orbifold cellular complex named by the Coast cellular complex, which is a special QCW complex introduced by Porter and Sucker. In this part, I will focus on explaining how to define orbifold boundary maps by blow-up. Finally, there are some examples of Coase orbifold and non-Coase orbifold. First, let's recall that what is an orbifold. The notion of orbifold is a generation of the notion of manifold, roughly speak. An n-dimensional orbifold is a singular space locally modeled on the quotient of an open set of Rn by a finite group action. See this picture. This is a sleeping teardrop. We denoted by X. The red part includes this isolated is the singular set. For these corner points, there is a neighborhood V, which is identified with a quotient space of D2 by a group Z22. So, and any points except this corner space in this loop is locally modeled to a half a disk. And expectively, this point it had a neighborhood which identified a quotient space of D2 by a finite cyclic group denoted by the rotation. So it is isolated. So this is the orbifold. There are 2 basic notions that is local group and underlying space. First, which is local space. Choose a point that have a neighborhood. If it is identical to its open set in Rn, and if this point previous of this point is orange, and this group is fixed the orange, then this final group is called this point is called the local group at this point. So this corner point has a local group is D22, and any point in this red line has a local group Z2, which is then generated by a reflection, and this point has a local group is a cyclic finite group, and another point has a trivial group. For the underlying space of X is an orbifold forgetting all the local group information. So next, let's look what is an orbifold. First, the Cook's group has a pre-relation like this formula, where mi equals 1. So its generators all have order 2, and if where mij equal 2 for all I don't equals j, then this Cook's group is called a right angled Cook's group. Every finite Cook's group is all finite Cook's group are classified by Coast, including the AN, BN in the talk of zone. And every finite Cook's group have a representation as a reflection group of Rn, and the orbit space is isomorphic to a simply solved cone at times Rn minus m, where m is the number of the generators of this finite Cook's group. So Cook's n orbifold is just an orbifold locally modeled to Rn divides a finite Cook's group. So because of this, so every Cook's orbifold is a manifold with corners in the sense of Davis. Next, let's review some orbifold homology series of orbifold. First, static generalized the Theorem cohomology to orbifold, and the Theorem cohomology of an orbifold is isomorphic to its the singular homology of its underlying space. So the Theorem cohomology of an orbifold cannot reflect the information of singular parts. And the next is the equivalent homology. If an orbifold can be realized as a quotient orbifold, that is, for example, a discrete finite discrete group act properly discontinuous and not freely on M, then its orbit space adheres a natural orbifold structure. Now we can define the orbifold homology of X is the homology of the Braid construction of G acting on M. We all know this Braid construction is always in infinity dimension. So this equivalent homology seems to be too large for an orbifold. The third is the Chen-Yuan cohomology of almost compact orbifold. And Chen-Yuan cohomology group is a direct sum of this, where T is the conjecture class of all elements in local groups, where x1 equal x is called the non-twist sector, and the other xg is called a twist sector, and its twist sector also provide the information of homology for this orbifold by a degree shifting number where is double Lg. Moreover, there are some other cohomology of orbifold. For example, the loop homology and T singular homology and in intersection homology and so on. Next, let's see what is a QCW complex, which is introduced by Porter and Saka, and recently is very Nussbaum and Saka and so on. The basic ideas of the Q complex cell is to take the quotient of a cell as a cell. So a Q cell is a En module divided finite group G. A QCW complex is constructed similar to the usual CW complex that is begin some discrete points and inductively attaching its n orbifold cell to n-1 skeleton. And the definition of the orbifold homology group or cohomology group of Porter and Saka is using the property this is held in CW complex, and they also have this. Moreover, this person studied the integral homology of QCW complex with cell in even dimensions. Well, let's see our Cox cellular complex. A Cox cellular complex first, where the Q cell, here is called Cox cell. Cox cell, then its local group is a finite Cox group, where En is called the blow up of this Cox cell. And if its local group is trivial, then we call this Cox cell is regular. Otherwise, it is singular. And with a little more requirement, our Cox cellular complex requires that every attaching map should be perceive the local group, that is this attaching map phi, restricting on the local groups of each point in this boundary of this cell is an isomorphism. This is very important in our construction. So under this condition, the boundary of a regular cell contains no singular cell. Let's see some examples. Here is a Cox 2 cell. It is a half disk, and this red is a singular part. Its boundary is an interval with two singular endpoints. We attaching these two cells to one skeleton, we can get the following. First, we attaching A have one zero cell and one singular one cell and one singular two cell. It is a disk which can be realized as S2 module, the quotient space of S2 with respect to Z2. And next is one zero cell and two singular one cell and one singular two cell. And C is one zero cell and two singular one cell and one regular one cell and this singular two cell. And D is two zero cell and two singular one cell and one regular cell. And this, moreover, this is a space if we attaching all the boundary to the pointer, to the single pointer, then we can get this. But this construction cannot perceive local groups because this is a regular pointer to this singular point. So E is a QCW complex, but not a cooked cellular complex. Let's define our orbifold cellular homology of cooked cellular complex. First, the orientation of each cooked cell is defined as the orientation of its blow-up. Then, naturally, the chain group is generated by the all cooked cell with dimension n. The key point is this: how to define the boundary map. In this talk, we defined it through the blow-up. Look at this diagram. This is a cooked n cell with local group W, and this is the blow-up. This is n-1 skeleton, and this is here. From we can see the boundary of this blow-up. We can get a n-1 sphere, and its sphere will through a quotient map to the boundary of this cooked cell, and this is attaching maps to n-1 skeleton. So in this way, we have the orbifold boundary map should determined by the attaching map phi, and quotient map determined by the local group action psi, and its boundary map parcel. So let's see when here attaching map is trivial. This is trivial. This is trivial means that this attaching map on this boundary of this cooked cell is injective. So we choose. So look at this the cooked two cell, the closed with this cooked cell, and this local group is a dihedral group. And this has the two zero cell and two singular one cell and one regular cell. This is a single. Look at this is the blue singular one cell in this boundary. It itself has a blow up like this. It's 1 and S1 is the index of its chamber, and this part the lifting in this bigger cooked cell it has 3 parts. It's U1, U2, U3. And each one can be represented by the chamber. For example, here U1 is 1 S1, U2 is 1 S1 S2, and S1 S2 S1. So we want to give a boundary map determined by this quotient map. The key point is how to give a corresponding relation from each cosine, this part to this part. They have different choice. For example, we can make 1-to-1 S1 to S1. Meanwhile, we also can make 1 to S1 and S1 to 1. Those different choices will influence our definition of the hierarchy. So the key point is how to give presentations of its coset, and its coset will corresponding to the lifting of this cells under the bigger cell, and this. This is the example. That is, if we choose the representation is S1, S2, then S1, S2 corresponding to 1, S1, S2, S1 corresponding S1. Otherwise, if we take this representation, then S1, S2, 1 equals to 1, and this corresponding to S1. Here, we give rules of the choice of presentation G of each coset. We require each G is chosen with the shortest word length. So now let the boundary map has a formula like this. Here is d beta is similar to the degrees defined in the boundary map in cellular complex. Then the each coset contributes this part to this debate, where LG is the word length of reduced G in this finite Coase group. Why here is the -1? That is because if we choose presentation is this, and to this G, and 1 to G, it should be through outer LG times reflection, and each times reflection will transfer 1 times orientation. So we had this is -1 LG. Of course, there is another rule of G. For example, choosing with the even word length, if purposely, then the associated orbifold homology is related to the weighted homology under some special cases. And in this talk, we only consider these rules. Under these rules, we can study how to define this debate. So let's say this debate is still trivial. That is, it continue this discuss. And we wanted to where debate equal to what? So if the bigger this is bigger, the Coase cell is trivial, then this cell just a regular cell. The regular cell contains no its boundary contains no the singular cell. So this defined this is just Euler boundary maps in CW complex. And if this is a singular Coase cell, and the boundary is a trivial cell, then since all the order of all finite Coase group is even, so where is the -1 LG is the pair of, so there has d beta equals 0. And the third case is if here is a singular Coase cell, and his boundary is also a singular Coase cell, then if the order of W divides the order of W beta is even, then they also paired off by this free -1 LG. Now its d beta is 0. Otherwise, if this part is odd, then it will lift a free -1 LG. Now the d beta equal to 1. Moreover, if the generators of W beta is less than the generators of W minus 1, then we can know from the finite Coase group this is always even. So this part is always d beta is equal to 0. Next, let us say when percent is trivial. Percent is trivial, it means that this is a bigger Coase n cell, and this boundary has the same local group. Now, look at this example. This part is a singular Coase 3 cell, and he has a local group Z2, and this gray part is its boundary, and this part is a singular point. Its boundary is a disk, and the boundary of this disk is a singular. And we take the two skeleton is this. It contains one zero cell and one singular 1 cell and one singular 2 cell. We attaching this to this. Then we can give a cellular decomposition for this disk and make each sectors to this. So now the local degrees can be equals to n beta, where n beta is the piece, is the number of this piece, which is also the degree of it. There is 1 to this was 1. So from these two examples, we can get an outlook to our orbifold boundary map. Our orbifold boundary map, this is where is n beta is determined by attaching map, and this part is determined by the cosine map, which reflects the local group. And if the rho of G is the difference, and this will difference, and this sum is determined by the parcel, of course. So we generalize our boundary map. Then our boundary map is in fact induced by phi, percent, and or parcel with orientation changer. These ideas can be used into many non-Coase orbifold. We will give an examples in the last. I think this will valued in all orbifold, but I can't give a classifier of all finite group acting on Rn. Next, let's introduce. Let's look the homology groups of Coase orbifold. Let X be a Coase n orbifold with admit a Coase cellular complex structure, and we take two faces of X because X any Coase n orbifold is a manifold with corners, so there will use the face. And we require that where f is the facet of f beta. So now each facet of X have a local group C2, which is generated by a reflection. If we denote this is SF, then any codimensional face this F in X will have a local group is a finite Closed group with generated by the all reflex SI corresponding to where this F intersected. So its face in a manifold with corners as a closed orbifold, it has a closed group, and if the closed group of F divides to the order, the closed group of F beta is order, then we give equivalence relations. So now we set T is a equivalence set of all face module. This equivalence relations. Then we can get this for any orbifold, closed orbifold, his S orbifold group is isomorphic to the direct sum like this, where Lg is the codimensional of the highest dimensional face in G, where G is the element in T. So it is an analog of chain rank cohomology group, because if we take G as the n face of X, that is underlying space, then it corresponds to Lg equal to 0. Now this is corresponding to the non-twist sectors in chain rank cohomology, and others corresponding to the twist sectors homologies in chain rank cohomology. And this formula is also analog of the host formula, because we defined the orbifold homology in terms of blow up. This blow up is locally, and the host formulas of the real moment angle manifold over a polytope is a blow up globally. In this orbifold, closed orbifold, in this integral homology groups, there are some different things where we take integral coefficient. First, we don't have this equation because this part, this is a closed cell. The more divides this boundary is well defined in our category, because this part it has a regular part and a singular part. We can't make this all to one point. This is not well defined, so we don't have this equation. And in some case, we also don't have this isomorphic. That is because the boundary map defined here determined by this, defined by the boundary of a closed cell, also named by the orbifold sphere, and its top homology may be not equal to Z, and it may be isomorphic to a free abelian group with a rank greater than 2, or have a probability. And although I think this is admitted in, but this is admitted in the definition of a closed orbifold. However, we have this formula that is all this chain group can be used as the relative homology groups. Let's begin. And we also have the Huawei theorem. We also can prove the long exact sequence of a pair, and this universal coefficient is also hot. The last is 3 examples. The first is a simple polytope equal with the right angle cos-orbifold structure. Then the standard cubical decomposition of this simple polytope is a right angle, the cos-cellular decomposition of P. Then now it's 8 orbifold fundamental groups is isomorphic to this orbifold fundamental groups of these 2 scalarity, and write it down. That is a right angle cos group of P. And the orbifold homology group of P, that's the Fn minus I, where Fn minus I is the number of the n minus I face of P. The second example is a cooled cylinder. Let Q be a solid cylinder with 3 faces. This F1, F2, and F3. Where F1, F2 intersects with F2 is this circle. We lambda by 2, which means its local group is D22, and this lambda indexed by 3, which means F2 intersects with F3 as a local group is a dihedral group with S1, S2, 3 equals 1. Then now it's solid cylinder is a cos-orbifold. Then we can give it a cellular decomposition like this. The only one cell and 3 singular 1 cell, and 3 1, 2, 3, 3, 2 cell, and this 2, 3 cell. We can get this homology group for this, and also we can use our series right x1 is just its underlying space is isomorphic to D3, and S1 means F1 itself, because this is 2, so it's this is 2, so F1 is not equivalence to this. So and have this, and S1 S2 is this, and the left S2 F3 and F, and this circle is a equivalence set in T, and it isomorphic is homeomorphic to D2. Now we can use our formula, write it down, is also this. The finally is example of non-cos orbifold. Let's add this as is a closed genus 2 orientable surface with 2 isolated singular points, and each singular points have a local group is a finite cyclic group generated by the rotation. Then we can give cell decompositions of this surface F like this. It has only 1 zero cell. Those 8 points will be glued to 1, and they had 6 regular 1 cell, and 2 singular 2 cell, and 1 regular cell. So we can write it all before the fundamental group like this. And now this homology group Fs is also can be computed like this. And in this case, the Huawei theory is also hard. That's the end. Thank you.
Thank you. Thank you very much. Let's thank Li Su.
Thank you.
Are there any questions?
I have one live question. So could you show me the page number 7, maybe? Yeah, so how do we know this En quotient by W is orientable or not? So is it always orientable?
Sorry. This.
So orientation of is defined as an orientation of okay. So this W action on this En is orientation preserving always or not?
Sorry, you slowly.
So my question is whether W action on En is orientation preserving action or not?
Not. It's a reflection, not a preserved orientation.
So for example, I'm thinking of an example like En when n is odd and W is just by maybe. Okay, so for example, real projective space may not appear in this example as a boundary of this cell.
Sorry. So I use this is reflect the information of its quotient type. So we define the D is by the blow up. That's the basic idea.
Okay. I will think about carefully again.
Okay. Thank you.
May I ask also something? Is there any ring structure, multiplicative structure in this orbifold cohomology? At least maybe in some cases, like when you have just this simple polytope, is there a ring structure in this Coxeter orbifold cohomology? Yeah, in this example that you've shown.
Yeah, this cohomology is trivial if this is a right angle same polytope, then this cohomology ring is trivial. Now we can
this is homology, but you may define the you can define cohomology similarly, I presume, yes? Can you also define cohomology? You were talking about homology of Coxeter orbifold, but I think that there is also cohomology, right? Orbifold.
Yes. All this is valid in cohomology.
And are you saying that there is a ring structure which is trivial in this case when you have a simple polytope?
Yes, the Keppel product in this case is trivial. Right. Well, not that trivial. That is this product is defined by the dual of the fixed, because this is Coxeter in simple polytope P is correspond is intersect transversely with a face with a codimensional for example K. Then this to the boundary of this in this group is just the intersection of intersection in face in P. So that is mainly because the all boundary map in right angle case is equal to 0. So we can define the cohomology ring by the intersection relation of the face of P.
Right. And what's the simplest example when this intersection ring cohomology or homology intersection ring is non-trivial? What's the simplest example? Just, well, yeah, I presume you can have just ordinary manifold, right? It's also a Coxeter orbifold with just, yeah, then.
We in general case, we are going to do this. So in this is XG, we can their cohomology comes from two parts where one part is from here T, and when another is determined this where is XG, but we can't give a equivalent couple product in this case.
All right.
Thank you.
Thank you. If there are no more questions, let's thank Lizu again. And yeah, we resume, I think in just 1 minute.
Do you see my screen?
Yes.
Okay, great.
All right, let's continue. Our next speaker is Mikhail Gorski, who will talk about braid varieties, torus sections, and stratifications. Please, Mikhail.
Yes, first of all, thanks to the organizers for the opportunity to give a talk. As it was said, I will talk about braid varieties, which I will define, and certain properties and results concerning these varieties, such as torus sections of them, and their stratifications. The talk is based on very recent joint preprint with Roger Casals, Eugene Gorski, and Jose Cimental, which appeared on the archive this week, I think on Tuesday. So this is very new. Okay. To talk about braid varieties, I first briefly remind you what braid groups are, even though you know this. So we have braid group, and inside it we have positive braid monoids with generators sigma I, which correspond to transpositions in some sense, but we do not require them to square up to unit, and relations which are all usual braid relations. So we have for neighbors we have a non-braid relations, and for far generators we have a commutation relation. And braid monoid is when you take only non-negative powers of sigma I without inverse. So when I will speak about positive braids all the time, we'll refer to some product of sigma i's, and in a sense we can think of Word and generator sigma I. Okay. Now to each generator of our braid group associate a certain matrix. Matrix is of a complex variable z. So it has a parameter, and it is a matrix which is slight deformation of the permutation matrix of corresponding transposition. So you see that z, if you send that z to 0, then you just get a permutation matrix. So bi corresponds to transposition of I and I plus 1. Okay, this is matrix for generator. We can also associate matrix for each positive braid. Namely, we take just product of letters in this positive braid word. And we will see in a bit, in a moment, how it depends on the word. But before that, I need to repeat that not only for generator, but for every positive braid word, this is a kind of a deformation of permutation matrix, in the sense that if you send everything to 0 and replace sigma i's by corresponding transpositions, then this gives you a permutation matrix of permutation that you obtain by product of these transpositions. So this is some kind of a deformation, and the lemma is that it more or less satisfies braid relations from the previous slide, but we need to change variables a bit. So namely, for commuting guys, the second relation here is the same. We do not do any change of variables, but for neighbors, we have some kind of a strange change of variable, which I will not speak a lot about, but it is relevant in the cluster story that will appear in the last slide, or maybe the previous to the last slide. But just see that if you forget i's, then you just get your permutation relations for generators. Otherwise, you need to do some change of variables. And this will be denoted by star. We will use this relation several times afterwards. So these braid matrices appeared in some disguises in various contexts. They were considered already by Euler in his study of continuance. I hope I pronounced this word correctly. But the point is that this some determinants of 3 diagonal matrices. And then they appeared in Stokes' study of irregular singularities, and more recently they appeared in works on so-called Stokes phenomena and wild character varieties, but I'm far from being an expert in this, so I won't say anything more. They appeared in works of Brouet and Michel on the Lustig varieties, and on works of Deligne himself on some braid invariants. And I presume that there were many appearances before and after. And quite recently, they appeared in a study of some Legendrian links, namely of certain Legendrian contact differential graded algebras. I will not define them, but I will speak about them in a few minutes. This was the work of Tamas Kalman. And a couple of years ago, Anton Mellet used these matrices and actually varieties that will appear on the next slide in a proof of the so-called curious-Lefschetz property for character varieties. I will say just a couple of words on curious-Lefschetz property. So the symmetry from usual hard-Lefschetz properties now is symmetry with respect to weight filtration. So grades, associated graded with respect to weight filtration has some symmetry. And this was introduced by, or better to say, this was conjectured in the context of character varieties by Hausel and Rodriguez-Villegas, I think 10 years ago or so, and recently proved by Mellet, using stratifications that will appear later. Okay, now that I hopefully convinced you that these matrices are not something random that we just decided to study, I will proceed to geometry. Okay, so sorry, I will proceed to geometry in a couple of slides. I changed the order at the last moment. So first, we have 2 examples. Which is probably for the best. One example is if we take what we denote by delta, very certain, namely lexicographically first in braid generators, lift of the longest element in permutation group, in symmetric group. Longest element is just cycle n-1, etc. 1, and it has such a lift. So this is a braid word. If we replace every sigma I by the corresponding permutation Si, and now use the fact that Si square is equal to identity, then we get a permutation, and this is the permutation. Then the matrix has such form. So if you put this variable z1 to z length of the word delta, and this is the binomial of just 2, then this is a matrix. Now assume that we took a different braid word such that it is also a lift of the same permutation, which is usually called half twist. Then by going back to this property, hopefully you see my pointer, we see that the product, it should be the matrix more or less of the same form, but you do some change of variables each time you perform a braid move. And you know that all reduced expressions like delta and delta prime are related by sequence of braid moves, like I plus 1, I2, I plus 1, I plus 1, and the other way around. And so the matrix also has similar form, but the entries are can be quite different, and there are some algebraically independent polynomials in our original variables. So this is an example of half twist, and what is full twist is the square of the word on the previous slide, and it has LU decomposition, and one can check that we have some parameters Cij and Uij which depend on Z and W respectively, but they are not just Z and W, they are something. But anyway, this is some nice matrix, and then the certain conditions that we'll put on Z's to define our braid varieties will give some restrictions on the corresponding matrices and so corresponding entries Cij and Uij. Okay, I'm on time. So what is a braid variety? Let me go a bit slower maybe. Take a positive braid word. Then we have a matrix B of beta for each braid word beta, and the condition is that the matrix is upper triangular in the complex space, well, of the dimension which is the length of the word, because this is the number of parameters that we put in. This is the number of elementary, not permutation, but these braid matrices that we multiply together. So this depends only on beta, and we can also consider permutation matrix together with this, and then the braid variety is defined by the rule that the first matrix, the one that we considered above, times p times pi is upper triangular. Now let me say that this does not depend on the choice of a word if two words are related by braid move. Indeed, this follows, by commutation move as well. This follows from the same relation. We do some change of variables, okay, but it's clear that the braid varieties will be algebraically isomorphic. And now we can we define these varieties, and now we can take a look at our examples from our previous slide. Namely, what happens if we ask B of full twist to be upper triangular? Well, we go back one slide, and we see that it's a product of lower triangular matrix times upper triangular. So the condition is precisely that lower triangular matrix has to be unit matrix. And then this is condition on Cij to vanish, but Uij are arbitrary, and so we have any Uij can appear, and so this is just C to the corresponding power, which is interesting. Okay, and the second easy example is half twist, where we multiply by permutation W naught, which is the longest element, and I will not explain this in details, but you can check that now this will be just a point. There will be no free parameters at all. So if you multiply this by the permutation matrix 1, 1, 1, 1, then you can check what happens and see that you get just a point. Okay. So these are two rather trivial examples, and one a bit more complicated is a braid that closes up to a trefoil node. So we take a braid on two strands. This means one generator. The only generator we denote by sigma 1. Delta is actually sigma 1 as well. So we can see the variety of our beta times delta square times full twist. Then it is the variety corresponding to sigma 1 to the power 5. And the condition is that this product is up a triangle, and I did not write lower index I1 because there is no lower index. We have matrices 2 by 2, so this is just B of something. So by performing several transformations, which I do not write, we obtain the following description. So first of all, this thing decomposes as a product of slightly more complicated variety in the sense that permutation appears times C, but well, the variety itself is not more complicated. It's just the definition is a bit more complicated, as you saw on the previous slide. And the second one is given by the following equation, or rather open condition in C3. So we have in principle 5 parameters, but we can rewrite and check that this lives in C3. And this variety is smooth, and we can also write it in a slightly different way by adding one parameter and sending it to 1, because we asked this sum z1 plus z3 plus z1, z2, z3 to be non-zero. Then we can ask it to remind its product with some new parameter to be equal to 1. And this will give us the same variety, only living in C3 times C star. So we see that there is actually a C star action on this guy, and the quotient is very nice. Okay. So this is, we could not see much on these two examples because, well, they are really elementary. You have just C to some power or you have point. This thing is more complicated, as you see. The more interesting variety, I will not draw anything about it. In our paper, you can see some Lagrangian skeleton of this guy, which I cannot even explain because one of the collaborators is symplectic geometry and he can draw these pictures, and I very vaguely understand them. But here we are. This equation I can understand. And this is two examples of what happens next, which are rather main properties of this story. So first of all, we always have a torus action. Torus action is defined by the following rule. So if you have T1, etc., Tn living in C star to n, then the action is given by this formula. And what are parameters Ci? Well, first of all, you have the word beta, sigma I1, etc., sigma IR. You replace these guys by elementary transpositions, Si1, etc., Sik minus 1. The last one is just permutation corresponding to our braid. And so we have a permutation, we have a sequence of permutations, and they define our parameters K, which are some products of neighbors in some sense inside T, the array T1, etc., Tn, but neighbors with respect to the corresponding permutation. So it's a bit tricky because you see that we do not just take Ik, but for example here, but we'll take Wk of Ik. But well, this is some action of a torus, and one can check that because of our braid relation star that appears a couple of times before, it preserves our braid variety x0 of beta. And actually, T, so diagonal C star living in this huge torus, X trivial on this variety. So we can quotient it out and get an action of a torus now n-1 on our variety. And one can check that the isomorphism that I mentioned, that we do have an isomorphism between varieties for different braid words of the same braid related by braid moves. But this isomorphism is actually equivalent with respect to this torus section. Okay, so yeah, this is the torus section. It exists. We won't go into details in what it is exactly. We will describe some properties of it. Let me check time. Okay, I'm on time. Okay, so we have some nice results concerning these varieties. And we will always do not take just beta, but take beta times delta or beta times delta square. So half twist or full twist will always appear. And I will explain later why. And because the main reason is that they are related to certain varieties that I mentioned briefly earlier, or maybe did not mention, namely some version of Bott-Samuelson varieties and also augmentation variety corresponding to this Legendrian link, which is a closure of our braid. And so these are reasons why we actually consider these kind of varieties. They also, precisely these varieties, I think, of beta delta appears in the work of Meillet. So this is another explanation why these are better than the rest. Okay, now the main result is on the slide is that these varieties are smooth and the dimension is quite clear. So it's length of our braid, and this guy is length of our blade plus binomial, and choose 2. And we have such a product decomposition, which is actually preserved by the torus section. So take a look at this product decomposition, and I will go back 2 slides back and see that we do have stuff like this appearing on the slide. Okay, so this is the explanation. This is the illustration of this product decomposition. This thing. Okay. And moreover, if the closure is a knot, so there is only one component, this is not a link, just a knot, then the action from the previous slide by C star n-1 is free. And if the action is free, then the very nice property is that the very nice consequence is that the quotient variety is also smooth and of dimensions that we can understand. Namely, we took the dimensions that we had and removed n-1 from them. Okay, reduce them by n-1. So we have the smoothness result, and next thing to discuss is relation to this Legendrian story. Namely, if we have a braid, then we can close it to a link, and actually one can always close it to a Legendrian ring in R3 with respect to some standard context structure. Then Chekhanov, 25 or so, maybe even more years ago, defined a differential graded algebra, associated a differential graded algebra to each Legendrian link. He started from any link diagram, so it's not necessarily a diagram which is a braid diagram, and proved that this thing is invariant of a link. What it is, it's a certain differential graded algebra that remembers also marked points on strands of our beta, or maybe on components of the link. So we have actually two natural choices of marked points. I will not go into details what this marked point means for everything, but they appear in the definition of this DGA. And then DGA morphism from this thing to C, considered as differential algebra, as differential graded algebra concentrated at degree 0 and with trivial differential. These things are called augmentations of a DGA, and all of them form an affine algebraic variety. So T now can be TS, TC, or something else. For any choice of marked points, reasonable some way, in some sense, we can associate this variety. And this is actually a phrasal of result of Kalman, is that for TS, for the choice of one marked points per strand of the braid, we get an algebra isomorphism to one of our braid varieties, namely beta delta for originally braid beta. So this is primary explanation, I would say, for us to consider beta delta and not just beta all the time, and more precisely x0 of beta delta and permutation, which is the longest permutation in this. And if we have, yeah, I'm sorry for the notation, T should be maybe different from T on the previous slide, but we can define certain algebraic torus for each, if we have TC, so namely, so we have one marked point per component, they live on some strands of our braid, and so we can define an algebraic torus sitting inside C star n by this equation, and we have an algebraic isomorphism like this, the last line, where we quotient out this torus. So I did not explain maybe too well what the torus is, but this is some part of C star n. It's not necessarily C star n minus 1. It's obviously C star n minus 1 if and only if we actually had a knot and not a link. So this is why one of the reasons why knot appeared on the last slide. Okay. So this is Legendre's story, maybe link story, and there is also a story from Lie theory, if I may, namely one kind of flags, namely so-called open Bose-Samuelson varieties. So if we have a positive braid word, then in the flag variety there are various sub-varieties. In particular, we have open Bose-Samuelson variety, which is a moduli space of tuples of flags, such that consecutive flags are in relative position SIK, and it means that everything before IK is the same, everything after IK plus 1 is the same, but in kth entry we have a different flag. So we consider full flags, obviously, and we have different flag in different subspace in dimension IK. And diagonal open Bose-Samuelson variety is a closed subvariety defined by the condition that we go back. So we change one flag at a time, and we go back. Change one subspace at a time, and we go back to where we start. Okay. Now the theorem is that our braid varieties also, in some sense, cover the case, generalize open Bose-Samuelson varieties. So if we fix our braid word and took standard Borel in JLN, then it acts freely on JLN times x0 of beta, and the section So better some natural map from JLN times x0 beta to diagonal open bottom variety induces an isomorphism where we quotient out by this action, by this free action. Okay, so our braid varieties recover augmentation varieties, at least with some choice of mark points, and up to some group actions recover diagonal open bottom varieties. And now I proceed to toric charts and stratifications. I have 11 more minutes, so I can describe it in a few details. So if we took a braid word with sigma I somewhere in the middle and just remove it to obtain a new braid word. So if we took something, then we had a letter, we removed it, and we have something else. Okay. This is usually called opening of a crossing sigma I in, or maybe i's crossing in, sorry, r's crossing in the braid word beta. And we have actually a rational map from our original braid variety for beta times full twist to this variety for one where we opened one crossing times C star. And it's actually an isomorphism between the right hand side and open subvariety defined by non-vanishing of the corresponding variable that are on the left hand side. Now we can compose these things. We can open crossings one by one and so on. And this thing is well defined. And so what does it mean? What will happen? We have a rational map from original braid to something star C times C star to something times C star square, etc., etc. And at the end, we will have just x0 of full twist times C star to the length of our braid beta. And remember that we had a full twist defined here, and it was just something nice. So we have a, sorry, yes. Okay, so we have a torus chart, toric chart in our variety. This is an open set, which is isomorphic to a torus in our variety, and one can actually check that this is stable under the C star to n-1 action, which we described a few slides ago. So these are toric charts, and they're stable under action of a certain different torus. So they descend to augmentation varieties in particular. And this toric charts are nice with respect to certain symplectic structure. To be more precise, we have some two form which is closed, and if we take a reasonable quotient by torus, then it will be a symplectic form, and actually holomorphic symplectic structure. So we have to quotient out by some torus, but the torus is given by taking one mark point per component in the closure of our braid. So we can define a two form. I don't give a definition, it's a bit long. And restriction is closed. And actually in toric charts, we have some canonical coordinates. And the two form has constant coefficients. So it's in some sense Darboux coefficients in the Darboux coordinates for this form in a toric chart. Here, tau of beta is some permutation of crossing. So we open crossing one by one, and we end up with just delta square, delta, whatever we started from, and we give a closed form. We get a closed form with nice restrictions to toric charts. And when we quotient out by corresponding torus, then we actually have a holomorphic symplexic form on the augmentation variety. Okay, so this was about holomorphic symplexic structure. And the last thing that I wanted to say about the toric charts is that they're related to cluster algebra story. But I did not write much on the slides, and I won't have time for much, so it's all works out. So first of all, we have a lot of toric charts, one for each sequence of openings of crossings, and the complement is of codimension 2, or maybe codimension at least 2. And this is a particular case of so-called cluster variety. What it means, what is a cluster variety is essentially a variety glued from tori such that transition functions are of certain very nice form, and volume form is can be defined globally. The special case of so-called affine log Calabi-Yau varieties. So for algebraic people, this means that the algebra functions on this variety, so maybe on cones over these varieties, has a structure of cluster algebra, but the definition of cluster algebra is a bit complicated and not super intuitive if you do not have this geometric toric intuition behind. So we have some tuples of formal variables, then we can mutate this tuple, which is called cluster, one by one. We change one variable by a certain rule, and then we can see the algebra generated by all iterated mutations of original variables. This some subalgebra of Laurent polynomials in original variables, which has very nice properties, and it's related to theory of canonical basis in certain coordinate rings and quantum groups, etc., etc. But what it boils down to is that, well, you had a canonical functions on a torus, and then you have transition functions to some other tori somewhere, and then you glue all these things together. Transition functions correspond to these mutations, then you glue them together, and you get some functions on something glued out of tori. If you are lucky, this is some nice variety. And obviously the story went backwards. People first had some nice varieties and noticed that transition functions between toric charts have very nice properties, and they're related by these mutations, etc., etc. And very recent theorem of, I think, this summer, maybe spring, by Gao, Shen, and Wang is that this variety and actually augmentation variety are cluster varieties. So I briefly explained what it means. Obviously, it's quite a long and complicated theory and very long paper. And then toric charts are precisely this cluster chart, so they correspond to clusters in a cluster algebra, which is the algebra of functions on this variety. And transition functions have very special form of cluster mutations. So this is everything about top dimensional strata, which are the toric charts. We can also want to find out what the complement to this codimension, what is the complement of codimension at least 2. And we can actually stratify these guys by strata described by a certain diagrammatic calculus. Diagrammatic calculus is quite similar to the orgal calculus of Elias Havanov or Elias Williamson, but instead of so-called associativity rule or associativity relation, we have a mutation So people who know a little bit about cluster algebras should remember that the basic example of cluster algebra is algebra functions on Grassmannian 2n, and clusters correspond to vertices of associahedron. So this is kind of related to associativity rules, binary trees, all this stuff. And this is where the main difference with Zergel calculus appears. But let me, in the last 2 minutes, show you an example of these diagrams. These are some diagrams glued out of trivalent vertices and 6-valent vertices, and maybe the so-called caps and cups. Where trivalent vertices correspond to braid relations. Oh, sorry, 6-valent vertices correspond to braid relations. Trivalent vertices corresponds to moves in some relations in Nilheke algebra, sigma I to sigma I. And cups and caps correspond to relations sigma I squared to 1 and 1 to sigma I squared. So each such diagram, if it can be drawn in this vertical way, defines a corresponding from the words on the top to the words on the bottom. The word on the top here is S1, which corresponds to blue line or blue strand, if you wish. S2, S1, S2, S1, S2, S1, S2, S1. So we had something like this, and we used all these braid moves and Nilheke relations to get just S2, S1, S2. And this defines a correspondence between braid variety for beta 2 and braid variety for beta 1. And actually, if we had no caps, then it defines an honest injective map. So this gives you some strata in the variety corresponding to this braid. And if we have only one generator, so 2-strand braids, then what this thing is roughly something very resembling a binary tree. If we end up in sigma 1, then it's always a binary tree. And then mutations are just the usual moves in binary trees in the so-called Tamara lattice. So this is what appears in stratification. But this diagrammatic calculus is maybe not so interesting for the topological part of the story. So I think I should not go into further details, and this is time, so perfect time to stop. I'm not show examples from the paper. Thank you for your attention.
Right, thank you. Let's thank Mikhail for his talk. And are there any questions, comments?
I have one question. So you described the torus section on braid variety. Is this section has some relationship with the torus section on the Bas-Samuelson variety?
On
Bas-Samuelson variety, there is a torus section. So
yes.
I wonder whether there is a relationship between the torus section on this braid variety and the torus section on the Bas-Samuelson variety.
Yes, I presume so. I'm not sure I can describe it well enough, but you see that some kind of quotient of G by B appears on the left-hand side. So this corresponds to the torus section on diagonal open Bas-Samuelson variety, but it's a bit tricky because you have also the quotient braid variety by Borel. If you understand what I mean.
Yeah. Okay. Thank you very much.
Yeah, I'm not sure if it was a clear answer, but there is a relation. Yes, you can check the paper.
Yeah. Okay.
And maybe it should be also written somewhere in the paper, which is called, I think, augmentations, filling, and cluster varieties.
Yeah. Thank you. I will look at the paper. Thank you.
And yes, and I think Mallet's paper on what is called cell decompositions of character varieties, I think is the title, where he speaks about Bot-Summerson as well.
Okay, I see. Thank you.
Yeah, I'm sorry. I'm using a laptop and not a tablet, so I cannot really write anything on the screen. And then this is not a good thing for explanations.
All right. Are there more questions? Well, if not, let's thank Mikhail again. And yeah, we resume in 11 minutes, 13:35 Moscow time.
Yeah.
SU linear operations in complex cobordism and C1 spherical bordism theory. Please, Georgi.
Okay, thank you, the organizers, for the invitation. And okay, there are three parts in my talk. In the first part, I will talk about SU linear operations in complex cobordism. In the next part, I will talk about C1 spherical bordism theory W. And in particular, I will discuss multiplications on it and projections from complex cobordism to W. And in the third part, I will talk about complex orientations of W and the corresponding formal group laws. Okay, SU linear operations. Consider the complex cobordism theory. It's defined by the corresponding Thom spectrum MU. And this theory has the natural module structure of the SU bordism theory. In other words, the spectrum MU is a module over the ring spectrum MSU. So we have a question. What is the structure of SU linear cohomological operations in complex cobordism? We have all cohomological operations and in complex cobordism, and which of them are SU linear? And first of all, what is it SU linear? What does it mean? We have two definitions of what is it to say that some operation is SU linear. The first definition is a categorical one. An operation f from mu to itself is SU linear if the following natural square commutes in the stable homotopy category. It's a usual algebraic definition of a module over a ring. And the second definition is geometrical. An operation f is SU linear if its action on the homotopy groups of mu is SU linear in the following natural sense. If we have a complex cobordism class M and the SU bordism class N, then the value of f as the product and M is just N f of M. So the action of f on the complex bordism groups is linear with respect to the multiplication by the SU manifolds. In general, the categorical definition, of course, implies the weaker geometrical definition, but one can check that in our case of MU and MSU spectra, these definitions are equivalent. That is, the geometrical definition implies the categorical one. And now let's consider some geometrically clear SU linear operations. It's an old geometric example of SU linear operations. So let phi be the stable Thom isomorphism in complex cobordism, which provides the bijection correspondence between the set of universal characteristic classes, the complex cobordism of BU, and homological operations in complex cobordism, the complex cobordism of MU. Yes, and so if we want to construct a homological operation, we can construct a characteristic class and then just apply the Thom isomorphism. Then consider the map determinant from BU to BU1, CP infinity, induced by the determinant map on groups from U to U1. And now denote by delta the characteristic class induced by this map from the first gen class. We consider the first gen class in the complex cobordism of CP infinity, and then we can induce induce from it by that the universal characteristic class delta in the complex cobordism of BU. Delta bar is induced from the bar first chain class, and the first chain class bar is just the inverse of the first chain class with respect to the formal group law. In complex cobordism, we have the formal group law, and then we have a power series in U bar, which is the inverse with the respect to the formal group law in this sense. And then the first chain class bar is just this power series in the first chain class. C1 bar of some complex line bundle is just the first chain class of the complex conjugate of this bundle. And now we have two characteristic classes, delta bar. And as was mentioned above, we can define the following homological operations following Sergei Petrovich-Novikov in the following way. It's just the Tom isomorphism of this product. These operations have a clear geometrical sense. Geometrically, the operation delta K1, K2 sends a Bordism class M to the class of the submanifold N dual to this direct sum of line bundles on M. The submanifold dual to the determinant to the power of K1 plus the conjugate determinant to the K2. And from this geometrical interpretation, we can obtain that these operations are SU linear, just because they are defined via the determinant, which does not depend on SU manifold factors. So we obtain the family of SU linear operations with clear geometric action. Now let's fix some notations which we'll use further. Delta is delta 1, 1. Sends to the submanifold dual to the direct sum of determinant and the conjugate determinant, and partial k or partial dk is delta k0, which sends to the submanifold dual to the determinant to the power of k, and partial d bar k sends to the submanifold dual to the conjugate determinant to the power of k. And now we can see that by definition of delta K1, K2, it's the Thom isomorphism of this product, but this product is just a power series in delta, because this delta bar is the power series in delta. And then we have this, and as a result, we have a series in partial decay. And hence, we obtain that any our operation delta K1, K2 can be expressed as a series in partial decay. And the other important thing is the action of these operations on the canonical orientation of complex cobordism. For the canonical orientation, we have the following formula. So U just multiplied by powers of U and U bar. And in particular, partial K decay had of U had this form. And it follows from this formula that if we have some operation which is expressed as a series in partial decay, then all coefficients alpha k we can uniquely recover it from the action of this operation on U. In other words, this expression is unique if it exists. And we see that it exists for our operations, but if we have this expression, it's unique. And now the theorem that in fact any SU linear operation has this expression. It can be uniquely expressed as a series in partial d k di with scalar coefficients. And the sketch of proof, first step, we have the map BSU to BU, B1 to BU, and plus in BU. And this map is a homotopy equivalence with the homotopy inverse of this form. We use here that we have the determinant map from BU to BU1, and we have the homotopy opposite for plus operation in BU and minus. And this map unique lift to a map to BSU, and this map to BU1, and this map in fact homotopy inverse to this map. And since this map is a homotopy equivalence, this map it induces an equivalence of the corresponding Thom spectra, and the induced map is of this form: MSU to MSU, and sigma minus 2 MU1 had the natural inclusion to MU, which corresponds to the canonical orientation of MU. And the module action of MSU on MU. And it's an MSU module map. In other words, we obtain that the spectrum MU here is equivalent as an MSU module to the MSU module of this form. MSU smash sigma minus 2 CP infinity. It's free or extended module with module structure from MSU factor and no MSU action on this factor. And we know that for modules of this form, we have the set of linear morphisms from the module of this form to any other module is in the natural bijective correspondence with the set of all morphisms from this part to the model, not linear but all morphisms. And we want to describe the set of MSU module maps from MU to itself, and it's in the bijective correspondence with just the complex cobordism of CP infinity. And one can check that under this bijection, an operation F goes just to its value at the canonical orientation. The complex cobordism CP infinity is just the power series in U, and since we know how partial dk acts on U, we see that these operations correspond to this power series. This power series is an arbitrary power series, and so we obtain that any, because we have a bijection, that any SU linear operation has this form. And we have seen above that we can express each of these operations as series in partial decay, not in partial bar decay. And this expression is unique. So the theorem is proved. Okay, and in the similar way, one can prove the following generalization of this theorem: that any SU multilinear operation in many variables, SU linear in each one, in complex cobordism had this form. It's series in products of partial decay. Okay, it was the first part about linear operations, and so the next part is about C1 spherical bordism. It's a bordism theory which is intermediate between complex and SU bordism theories, and it naturally arises in calculation of the SU bordism ring. We consider the C1 spherical bordism theory W. It's a bordism theory of compact manifolds with the following additional data. The first is a stably complex structure, and the second is a CP1 reduction of the determinant bundle. That is, in general, the determinant line bundle is classified by a map to CP infinity, and a CP1 reduction is a map to CP1, which also classifies the determinant bundle if it exists, of course. And for example, a CP0 reduction is just a trivialization, and the trivialization of the determinant bundle is equivalent to an SU structure, and hence it's a natural generalization of an SU structure. Okay, this is spherical. Homotopically, a spherical structure on a stable complex bundle Xi is defined by a lift of Xi to a map M to X, where X is the homotopy pullback of this diagram, BU determined to CP infinity, CP1 inclusion to CP infinity, and X is the homotopy pullback. If here is CP0, then X is just the homotopy fiber of that. That is BSU, and it's an SU structure again. And the Thom spectrum of the map X to BU defines the C1 spherical bordism theory, and we will denote it by W theory and W spectrum. And we have the nature of forgetting maps of MSU modules, MSU to W to MU. And now about connection of W with operation delta. Robert Stong geometrically defined the operation pi0 from the complex Bordism groups to the C1 spherical Bordism groups, which sends a Bordism plus M to the class of the submanifold N in the product of CP1 and M, due to the tensor product of the canonical bundle over CP1 and the determinant of M. This submanifold has the natural C1 spherical stable complex structure because its determinant bundle is isomorphic to the restriction of the canonical bundle over CP1 to the submanifold N. And Stong geometrically proved the following proposition: the composition of the forgetting map and pi0 is the identity. In other words, the forgetting map is injective and its image is a direct summand in complex Bordism group, and we can project complex Bordism group onto the summand by pi0. We call pi0 the Stong projection. This projection can be expressed at the following series in partial decay. Alpha 1k are here the coefficients of the formal group law of complex cobordism. Okay, now if M is C1 spherical manifold, then the direct sum of the determinant and the conjugate determinant is trivial because the determinant is induced from CP1, and over CP1 the direct sum of a line bundle and its conjugate is trivial. Hence the operation delta, which sends M to the submanifold dual to this sum of line bundles, is 0 on W. And conversely, one can check that vanishing of delta or partial decay can be described in terms of vanishing some Chern numbers. And from this, one can obtain that higher partials are 0 if delta is 0. And hence, from this formula, we obtain that pi0 is the identity on the kernel of delta, because in the kernel of delta, all higher partial k are 0. And we obtain that the image of the forgetting map, as a result, coincides with the kernel of delta. And from this, we can obtain the following homotopical description of W, that the spectrum W is the fiber of operation delta in complex cobordism. And now we have the following fiber sequence, and mapping it to the spectrum W, we obtain the following exact sequence, and projections from MU to W are operations here that maps to the identity here. And two of such projections differ by the image of some operations from here. And as a result, we obtain the following proposition. Okay, let pi be an arbitrary projection from U to W, then any other such projection can be written in this form: pi 1 plus f delta, where f is an arbitrary operation. And furthermore, if pi is SU linear, then all SU linear projections can be obtained from SU linear operations f. And on the other hand, if we regard the projections from U to W as operations in complex cobordism via forgetting from W to complex cobordism, we obtain the following proposition: such projections have the form 1 minus f delta for an arbitrary right inverse f of for delta. If we have a right inverse, it's a projection, and if we have a projection, it can be written in this form. And moreover, different projections correspond to different f, and SU linear projections correspond to SU linear f. It also obtained from the fiber sequence above. And now it was Peter Corner and Edwin Floyd who originally introduced the subgroup of C1 spherical Bordism in complex Bordism group, exactly at the kernel of the operation delta. And they geometrically defined the right inverse operation for delta, which was extended to a homological operation psi by Sergei Petrovich Novikov. And thus, in the standard algebraic situation, when we have the hypermorphism and its right inverse, and we have a standard way to define a projection onto the kernel of the hypermorphism, exactly of this form. And Conner and Floyd defined the projection, and they defined it on the homotopy groups, but it has the extension to the homological operation, and we have this projection, which we call the corner-Floyd projection. And this projection don't coincide with the Stonk projection. But there is the thing which is the same for them. Any projection from U to W defines the bilinear multiplication on W by the following formula: forgetting, multiplication in MU, and then projection. But the statement that it's a bilinear operation for any operation pi here. And but the statement that pi is a projection on W, it's the identity on W itself. This statement is equivalent to the statement that this multiplication has the standard unit. The standard unit is the unit which is obtained from the unit in MSU by forgetting. We have the unit in MSU and we can forget it to W, and we say that the multiplication has the standard unit if this element is the unit of this multiplication. And this multiplication has the standard unit if and only if this operation is a projection to W. And if pi is SU linear, we obtain the SU bilinear multiplication. And we have the following description of multiplication obtained from some projection in this manner. Any multiplication obtained from a SU linear projection has this form. The usual product in MU, no, after forgetting, the usual product in MU and this additional summand V, where V is the fixed element, is the coefficient of the formal group law alpha 1, 2 in complex cobordism. And W is some deformation summand by which multiplications differ. If a multiplication is defined by an SU linear projection pi, then W is just the value of pi at V. And if we express pi via the Stonk projection of this form, then W is pi F1, and in particular for pi 0 itself, for the Stonk projection, F is 0 and then W is 0, and the multiplication have the form without W here. It's the multiplication defined by the Stonk projection W. And in fact, any projection pi can be written as the series of this form, 1 plus these terms without partial D1 term. And if pi is expressed as this series, then the corresponding multiplication has this form. This coefficient is just alpha 2. And one can check that the corner-Floyd projection, the Stonk projection define the same multiplication on W. In other words, they have the same coefficient alpha 2. But other coefficients are different, but alpha 2 is the same. And the same. And as we know, SU bilinear operation in MU, we can obtain the following result about all SU bilinear multiplication on W. Any SU bilinear multiplication with the standard unit has this form. All such multiplication are associative and commutative. And such a multiplication is defined by an SU linear projection if and only if this summand is divided by 2. In this case, here we have a common 2. And here we have 2 only with B, but W without 2. And if W is divided by 2, we have a projection defined by an SU linear projection. Okay. Okay, that's and now the third part of my talk is about complex orientations of W. For any SU linear projection pi and any
Georgi, we can't hear you. Hello? Денис?
Да, здесь.
Так, а что-то Георгий пропал, или это у меня пропало? Я.
Алло, Тарас Евгеньевич, меня слышите?
Да-да-да.
Да, у него свет отключили.
Oh, all right. Yeah. So
Наверное.
we have a problem. There was a kind of blackout at the place where George is living, so he cannot access internet at the moment. So we can wait a couple of minutes, maybe. Hopefully he can reconnect.
I think there's nothing we can do about this for the moment, right?
Yes. Things happen. Yeah. Okay, I can try to phone him. Yeah, all right. I've just talked to George on the phone, yeah, and he still doesn't have electricity at his flat. Yeah, so I think we'll need to finish this session at the moment. Hopefully he'll rejoin us in the afternoon session and he'll share his slides and we'll post it in the chat. But
I think we also could just in a separate Zoom meeting finish his recording for the video of his talk at least to be available.
Yes.
Or a full video of his talk to be available.
That's right. Yeah. Okay. So well, unfortunately, we need to finish this session, and yeah. So hopefully, as I said, George will rejoin us and he'll be available for communication and for questions in the afternoon session. So yeah,
should we do this before the beginning of the evening session?
Well, no, I think yeah, we just started scheduled, and then we maybe in the breaks we can. Yeah, the recording. You mean the recording? Yeah, you can.
Yeah, I mean, the recording, we can do it whenever we want. The problem is that it will be uploaded to the mat-net site, at least I say, in several days, at least 4 or 5 days, I think. So I think it's not a problem to finish the recording, but it's not an immediate, this will not give you an immediate result. Yeah,
that's true. All right, so we resume at 5 o'clock, 17 hours, 5 o'clock p.m. Moscow time, roughly in 3 hours, slightly less than 3 hours from now.